Am I? Yes, I'm on. So I'm Thomas. I'm a developer at Goldmund, Wildebeest, and Wunderliebe. I work in Amsterdam, actually. And I'm going to tell you something about generative adversarial networks, which are a type of neural network used to generate realistic fake data. And because every good presentation starts with some audience interaction, we've already had a bit of a day. So I want to start with a little game. And I'm going to show you some images of human faces. And some of these are computer generated. And I want you to tell me which ones they are. So let's start with these two. Who thinks the person on my left is generated by a computer? So that's that one. OK. And the person on the right? It's about 50-50, I guess. And then the next one. So who thinks the person on the left is computer generated? OK. And the person on the right? OK, last one, I think. So who thinks the person on the left is computer generated? Few people. And the person on my right? Well, I think I heard somebody say it already, but almost all of these faces were computer generated, except for this person on my left. Because that's actually Ian Goodfellow, who developed the first generative adversarial network. And all the other images were by a network made by NVIDIA called StyleGAN. And you can actually, if you go to thispersondoesnotexist.com, it generates a new face for you, and that's where I got these faces from. I just pressed refresh a few times, and it made these images for me. What StyleGAN can also do, for example, is style mixing. So on the left here, you see a changing generated image, and it combines it with the images on the top to change the gender or the hair length or the age of the person on the bottom left. So that's pretty cool, I think. And now something about the history of generative adversarial networks. So this is Ian Goodfellow. He's real. He's not generated. And like all good ideas, the idea for the GANs started with a discussion at a bar. So Ian was, I think he was out celebrating somebody's PhD dissertation, I'm not sure. And they were having a discussion about generative networks or generative machine learning. So these are machine learning models or neural networks used to generate fake data, basically. And up until then, well, there were some generative models, but they were not very good. So they were discussing how can we make this better. And Ian came up with the idea for generative adversarial networks. And that night, he didn't sleep before he actually developed the first working GAN, so that's pretty cool. And since then, it has really taken flight, and it's really a hot topic in machine learning. People are still doing a lot with it, mainly in the visual domain. The main idea, OK, so a little bit of well, it's fine. The main idea is that you have two competing artificial neural networks. You have a generator and a discriminator. And they have two competing tasks. So what the generator does, it tries to generate realistic fake data in a given domain. So if we take the fake faces, it tries to generate fake images of faces. What the task of the discriminator is that it gets real samples of real faces and fake samples of fake faces, and it has to find which ones are fake and which ones are real. And these two networks are constantly updating each other. So at first, the generator creates random nonsense, and then the discriminator has a real easy time making a distinction. And based on how the discriminator does, the generator is updated. So then the generator becomes better, then the discriminator has to try harder, and it becomes better, etc. And it's often compared to the counterfeiting of money. So in the counterfeiting of money, you have two sort of teams. You have the police, and you have criminals who are trying to make fake money. And the criminals are paying with real money, but sometimes they slip a fake note in there. And at first, they're very bad at it. It's just a hand-drawn thing or a thing they made in paint. So the police has a very easy time to see which ones are real and which ones are fake. But over time, these counterfeiters are getting better. So the police has a harder time to distinguish which ones are real and which ones are fake. So they improve. And that's basically the idea behind GANs. And as I said, it's been mostly applied in the visual domain, so with image generation. The images you see here were generated by Pygrunn, which was developed at Google. And Pygrunn is trained on the ImageNet dataset, which is a dataset with a lot of images in a lot of different classes of, well, wolves, and they have like 50 types of dogs, I don't know. And what they did at Pygrunn was they trained a network on this data set, and now they can generate very high resolution and high quality fake images. So what GANs suffered from before was that the images were quite all right, but they were very low resolution. And because this was developed by Google, well, they had a buttload of servers, so they just had way more processing power, and they could train way bigger models. Another example is a little video I'm going to show you. This was developed by NVIDIA, and it's called GAN, and they made a tool called Spade. That's not what I tried to do. Let's see if this works. It does. Does it? Yes. So what you see here on the right is somebody drawing with a kind of semantic paintbrush. I hope, at least. Yes. So this person is drawing C, and you see on the right that the network automatically generates photorealistic images from these, well, kind of stylistic representations that are painted on the right. So now he paints in a rock. Look, there's a lovely rock. Maybe make some mountains in the background. You can change the style. And these are just two small examples of what you can do with generative adversarial networks. Let's see if this stops now. Yes. And there's also other examples that are not as visually interesting maybe, but that are interesting in other ways, because GANs have also been applied for fraud detection, which might seem, well, generating fake data and then recognizing that fake data, that might seem like it makes sense. What they did here is pre-train a network with just, because the issue in fraud detection is that there's not a lot of examples of actual fraud. If you build a data set for, I don't know, banking fraud or fraud on eBay, you usually have a lot of examples of real transactions, but not a lot of fraudulent transactions. So using GANs, they could train a network to only train on real examples, and in the end, it had a very good results on fake examples as well. Yeah, so let's go a bit more in depth on how this works. This is similar to the image you saw before. So you have a generator and a discriminator and real data, and the discriminator then has to say if it's fake or if it's any of the real classes. And the generator gets input noise and then tries to make real data or realistic fake data from that input noise. So let's first look at the generator. So this is a kind of GIF of the process of training of a generator. It's not a very good GIF, but believe me when I say that it starts out with random noise and then it generates kind of realistic looking photos of images. And the way in which this works is it uses something called, well, sometimes called deconvolution or fractionally strided convolution. And this is basically the inverse of, I don't know how many of you were at the talk before about image recognition in Python and computer vision. Well, not many, but some. Anyway, the speaker explained convolutional neural networks, which are networks used for image classification. And this works in an inverse way, basically. So you have an input vector on the left, and that input vector is then, by strided convolutions, it's ultimately made into a bigger picture. The discriminator works in exactly the opposite way. So the discriminator is actually just a regular convolutional neural network, which is used in all kinds of computer vision tasks. And it basically just does a standard image classification task. So it has to maximize the probability for the real images and minimize it for the fake images. So what that means is it has to find values close to 0 for fake images and values close to 1 for real images. And it just, well, you can just use things you would use in every image classification task, basically. So you get 2 images, and you have to say to which class it belongs. Is it a real image? Is it a fake image? There's different flavors of GANs that are, and I'm going to focus on 3 of them. So you have the basic GAN, which is basically what I explained to you before. And then in I don't know when, somebody designed a DC GAN, or a deep convolutional GAN. And this is basically just an upgrade of the regular GAN. So they use some tricks to make it better. For example, they changed the fully connected hidden layers with deeper architectures. So they make it a bit more complicated. They used a bit more batch normalization, max pooling. Well, it's not that important actually, but usually when you see people talking about GANs and people implementing GANs, DC GAN is kind of the go-to now. That's the standard. Then you also have the WGAN, or the Wasserstein GAN, which is an extension of the DC GAN, and that uses the Wasserstein distance, the Wasserstein, distance, and it's an extension of the DC GAN. And learning with a WGAN is a bit more stable than with other GANs. And the loss that you get from a WGAN also relates to the image quality. And finally, you have the CC GAN, that's sometimes also called the C-GAN. That's the context conditional GAN. And that's a GAN that gets some context. For example, you have a face, but only the eyes are left out. So you have the context of the face in your image, and then the GAN has to fill in the missing gaps. So this can also be used for image restoration, for example, or for sharpening images. It's used in cases where you have some information already, and you have to fill in some extra information with, well, unknown data, basically. There are some issues with GANs, or some things to keep in mind, mostly. And one of the first ones is mode collapse. So in machine learning, one of the data sets that's used often as a sort of for toy problems, for example, is the MNIST data set. And that's a data set of written numbers. And this is something generated by a GAN that was trained on the MNIST data set. And, well, something that might stand out is that it's just 2 different numbers. And that's what we call mode collapse, where the GAN only outputs very similar, but nonetheless convincing output. So for faces, it could be that it only makes 2 very convincing faces that are nonetheless the same. Because, well, this is pretty realistic for the MNIST data set. The 1s and the 8s actually look somewhat like this. And the way you can solve this is by not giving the discriminator 1 of each. So you give it 1 fake and 1 real sample, but you give it batches of real and fake samples. So you give it batches of a few real numbers and batches of a few fake numbers. And if it gets a batch of only 1s and 8s, then it knows, oh, this is probably fake, because I see no other numbers here. Another issue can be that it actually just memorizes the training data. The top images here are images from the style GAN that I showed you in the beginning. So those are generated faces. And they calculated the distance to the closest example from the training data. So that's a way that you can see if it actually memorized the training data. And if those images are too similar, well, in this case, I wouldn't necessarily say so. The 2 images on the right or on my left are very different. Those are not the same person. But if you do have the issue where it actually memorizes the training data, you can use different data deduplication processes. And it's basically just overfitting, which is a common problem in machine learning, where your data set is either too small or your parameters are not good enough, so you only get into local minima, basically. Or, sorry, that's not true. Or so your output looks based too much on your training data. Another issue is that it's very hard to fine-tune GANs, because you have 2 neural networks that are competing with each other. They have a lot of interaction. They are pretty, well, sort of complex networks. So it's hard to find the right hyperparameters and settings. So that's something to keep in mind. There's not one standard way to fix this. It's just something, well, that's usually a lot of work. Another issue is that one of the networks might overpower the other network. So you have the discriminator and the generator, and they're basically competing in a game. But it can happen that one of them is too good at its task. So if the discriminator is too good, it can always distinguish between fake and real data. It can always say, oh, this is fake, this is real. And the loss you get from that, so the information it gives the generator is not useful because the generator doesn't know when it's doing better or it's doing worse. It's just doing bad all the time. So how do you improve then? It can also happen the other way around, that the generator is constantly exploiting weaknesses found in the discriminator. And then, well, this is not very useful info for the discriminator. But luckily, there's ways to overcome this problem. One of the ways is to pre-train your discriminator, and maybe, well, you can't really pre-train your generator, unfortunately, but pre-train your discriminator so it has a decent baseline performance. So at least it gives some useful information. It's not just blind guessing. And usually you train the discriminator and the generator against a static adversary. So you train the generator while you keep your discriminator the same, and you train your discriminator while you keep your generator the same. And there's also other ways. The Wasserstein GAN that I mentioned before doesn't really have this problem. Anyway. Another, well, not really issue, but thing to keep in mind is I've mostly talked about image examples now of ways to generate realistic-looking images. But GANs have also been applied in other fields. They have been applied to make music, for example. I told you about the fraud detection. And one way in which you might want to use this is to generate text, to generate fake texts. But unfortunately, this is not possible because GANs are only defined for continuous real-value data. So if you think, for example, about an image, and a generator generates a face, then the discriminator can, well, it's not exactly how it works, but sort of say this pixel is not good, it needs to be 0.1 bigger or smaller. But for text, you can't say, oh, this sentence is a very good sentence, but this word needs to be 0.1 or a very small fraction of a bit bigger or smaller. That doesn't really make any sense. And there are ways, some sort of ways to represent text in a continuous way. So, well, some research is going into this, but it's not very good yet. And, well, I'm not sure if it's ever going to be good. Another issue that I do have a slide for is about the evaluation of GANs. Because, well, it really depends on the goal of your GAN, but when is your GAN good? Is it good if it creates data that can fool the discriminator every time? Because that can just mean that your generator is too good or your discriminator is not good enough at that point in time. Do you want to actually create images that are very similar to the training data or not? So evaluation is not really straightforward and really depends on the task. And one last issue is, well, a very common issue in machine learning, that even though you are creating fake data, you still need a lot of real training data. And your results also depend on the quality of your training data. Now I want to talk a bit about how you can implement this in Python, because we're at Pygrunn, so that seemed to make sense to me. And like most machine learning things, you can use your favorite Python machine learning framework, and it will work just fine. So I think the two most common ones are probably TensorFlow and PiTorch. You also have Keras, but that's basically included in TensorFlow now, so I left it out for this comparison. And I think what it really comes down to is personal preference. I like TensorFlow because I use it a lot. I know there are people who really like PyTorch. And, well, there are some upsides and downsides to both of them. I can go through the list very quickly. TensorFlow is, well, it's used by much more people, so you have much more examples, for example. But PyTorch is really a growing community, and maybe that's exciting for you. TensorFlow, for example, is pretty difficult to debug because you can't use your standard Python debuggers. While with PiTorch, you can just use IPDB or whatever you like to debug it. TensorFlow has a really nice visualization tool. It has a deployment tool. I think there's even a specific package that deals with GANs, which is not in PiTorch yet, as far as I know. So yeah, well, it really depends on what you want. I can't really tell you which one is better. Yeah, now I want to show you some small code snippets of a GAN that you could use to generate MNIST examples, because this is the MNIST data set again with the written numbers. You don't really need to understand all of it. I just wanted to give you an idea of what it could look like. So let's look at the generator first. And if you've worked with TensorFlow, and especially if you've worked with convolutional neural networks, so with computer vision, this might look very familiar, and that's because it is actually. So I told you before that what the generator does is basically the inverse task of what a standard image classification model does. So you see here the standard convolutional layers, you see dropout, you see batch normalization. I think this is a DC GAN network, so it has all the newest tricks and bells and whistles. For the discriminator, well, this is just a standard model that you could use in your everyday image classification task. So it's just a convolutional model. This is a very simple one because MNIST is a very simple data set, but you could make it as deep as your task needs. You can use transfer learning, so learning a pre-trained network and building your own network on top of it. Whatever you like. Then you need to set up your losses. You need to make noise for your generator. You need to set up your optimizer, and this just all depends on your task. I think there are some loss functions and some optimizers that are more useful for GANs than others. But once again, it's ultimately just image classification versus image generation. So the loss is not really set in stone. And then you need to train it for a certain amount of epochs or until it converges. So what they do in this example is they mix training the generator and training the discriminator based on how well the other one is doing. So if the generator is doing too well, they don't train the generator and only train the discriminator. And if the discriminator is doing too well, they only train the generator, etc. And they have a discriminator for fake and for real data, so they have two separate losses that they can use to train both the generator and the discriminator. One final thing I wanted to get into is an issue with resources. So these are images from Big GAN again, the Google network. And one of the reasons why it's really top-notch is just because of all of the resources that Google has. That's not just my opinion, that's also the opinion of the person who made Big GAN, who said it's not really very interesting architecture or that he did anything super smart, but he actually made it during his lunch break, I think, and he just had all the server power of Google and all the data of Google that he wanted. And similarly, all the nice NVIDIA tools are also mostly popular because they just have, a boatload of data, a boatload of processing power. They probably have a very nice GPU room or whatever they have. You probably don't have that at home or maybe not at your company, but there are some solutions to that. You can use cloud services to train your machine learning on, for example. Google gives you access to their tensor processing units, which are specifically designed for machine learning training. So that could be a solution. You could spend a lot of money on buying very expensive GPUs, but at least it's something to keep in mind. And as I said, GANs have only really been around since 2014, so it's relatively new. So there are super exciting things that are made, almost every month there is a new cool paper about using it in video, using it to generate new and exciting sounds. I recently gave a talk about GANs in art. There's a whole generative art scene now, or it was there before as well, but that really got a boost. So it's all very exciting stuff, I think, and I hope I made it exciting for you as well, and I think that's it.
Thank you. Any questions from the audience?
Do you perhaps know if Deep Dream is also
yeah, that's
GAN?
also made by GAN, indeed.
Ah.
It's I think it was one of the earlier ones as well. And Deep Dream, for people who don't know, well, you should look it up later. It's very cool. It uses style mixing, so you can upload an image or choose an image of yourself, for example, and then choose a very famous artwork. And it combines the style of that artwork with your picture. So I've been painted by Van Gogh and by, I don't know, in the style of the Great Wave of Kanagawa. It's all very cool stuff. And it also makes these very weird kind of fractural dog pictures and stuff. And it's, yeah, super cool stuff. And it's also made by GANs, indeed.
Yeah, it's really cool.
In one of the slides, I saw a list of dogs that were generated.
Yeah.
One of the dogs, that one with the red, doesn't seem to be becoming very correct.
No, some of them are a bit sick, indeed.
Yeah.
So
What does that cause?
Yeah, well, just it's not always great quality. What you see here in this GIF actually is so an interesting aspect of GANs is that you can actually tweak individual features by tweaking the input vector, I think. So here they're changing the input vector, and that has effect on the pose of the dogs or the type of dog. And sometimes it just gets into this weird, very creative, artsy phase. I think the big GAN author initially published results on Twitter as well, and one very famous one is the, I can, wait a second, if I can show you, was the dog ball. Yeah, there it is, which is a very cute, oh, sorry, Jesus. Tennis ball dog. So yeah, sometimes you get these weird artifacts, and it just depends on the quality of your network. And
what did he do? Did he put a tennis ball in the algorithm and a dog?
No, I think this was just a mistake.
Oh.
It's I don't know. The algorithm got confused. I think it's also because ImageNet, maybe the data is a bit noisy, and there was also a tennis ball in there. I'm not entirely sure how it came to be, but
Okay.
it's just mistakes, basically.
Okay. But can I ask one small question?
Sure.
All the stuff that he puts in one image, they all have the same weight, right? Or are there some images that have more weight? For example, the tennis ball, could it have had more weight than the other ones, so that it had a bigger
No, I think for
effect
Big GAN, it's really class specific. So it generates dogs if you wanted to generate dogs. It's not like it will generate a random class or something. So I think it's all. So I'm not entirely sure if that answers your question. It's not like sometimes it gives you a tennis ball, sometimes it gives you a dog.
Hij gebruikt, it's using a whole array of different images to come to one image, right?
Not really. You train it with different images.
Oh, okay.
But it just outputs one image based on just random input noise.
Okay.
So
Thank you.
not really. There's a question here as well, I think.
I was wondering about the generator. So
Yes.
how you start it up. Does it at first truly give just random noise, and then the discriminator has to distinguish between the random noise and the real input images?
Yes,
Or-
basically.
Yeah? There's no kickstarting there that you have to do in order for it to make it...
No, there's probably tricks that you can do kickstart it, but for at least for the smaller problems that I worked on, it works fine if it just inputs random garbage.
It feels like it's too easy for the discriminator to distinguish between a real class and
it is
noise.
at first, but at first it's also often a discriminator that's not very good, so then you still get sensible feedback. It doesn't start with a fully trained discriminator, because in that case you would get
stuck.
nonsensical, you would get stuck basically.
Oh, okay, thanks.
Okay, final question, I believe.
Hi. Is it possible to train the input vector parameters for a generator to be bound to a certain feature, like looking left or right? Like, can you? I've seen in some of the generators where you can tweak and the character moves.
Yeah, I don't
side,
think
but can you actually make it do that?
You can make it do that, but not by training it in a certain way. But I think it depends on the input vector you give it. I'm not entirely sure how they do that, to be honest. But it's all the same generator, the same trained model. But there's ways to, I think, change the input vector in such a way that you can actually alter, for example, the pose or the hair color. So that's the interesting part, that certain features correspond to certain semantic features as well, if that makes sense. So it's all the same model, but there's just ways to change those semantic features.
But you discover that after the fact, after the training, or can you direct the training to generate certain semantic parameters?
Well, ultimately, your generator can output whatever, but you can then change the input so it gives a certain angle for the photo, for example, or a certain type of hair. So it doesn't really depend on the training, but it depends on the input you give it.
Well, that wraps it up. I'd like to thank Thomas for a great talk, I'd say. Thank you.